Hello again, everyone. Welcome to Homeport. We've got another day of demonstrations for you. These are being live streamed into the Congress and are also available on YouTube, so be sure to check those out afterwards. To start the day, we're going to have RoBoVaaS, who are demonstrating their service platform, which is an unmanned vessels as a service for maintenance and inspections in ports and near shore. We're going to start with a video, and then Vincent Schneider from Fraunhofer, CML, sorry about the pronunciation there, he's going to talk us through the presentation and demonstration, and then after that we're going to have a short panel. So maybe starting with the video, and then over to Vincent. Thank you.
As the world becomes increasingly digitalized, so are ports and maritime transport. Sensor data collection is increasing safety and security measures and operational efficiency, whilst technologies will continue to reduce accidents, economic costs, and carbon emissions. The Robotic Vessels as a Service, aka RoBoVaaS project, is about demonstrating services that connect cloud-based software infrastructure, a fleet of autonomous vehicles, and innovative sensor and inspection technologies to show the potential of on-demand maritime robotic services for larger-scale deployment. When a user requests a service via the RoBoVaaS cloud, autonomous surface vehicles, ASV, are deployed to collect data for the given service that is relayed back to the cloud. Possible users include ship captains for anti-grounding, ship owners for hull inspection, port authorities for key wall inspections, or terminal owners for data collection. The RoBoVaaS demos include 5 services that provide data to the users. Ship hull inspections using the remotely operated vehicle, ROV, launched from the ASV, can inspect and locate possible damages precisely without any risking diving operations. Key wall inspections can be performed by both ASV and ROV as routine inspections with high detail sensors, thus reducing the operational costs dramatically. Data muling relies on underwater acoustic communication to transmit data, which is useful in port areas where buoys or tethers can be obstacles to vessels. Bathymetry data collection uses ASV to map depth deviation from nautical charts, allowing for up-to-date information in areas with high tidal variation. Anti-grounding has an ASV traveling ahead of a vessel and collecting depth data in real time. Depth deviation from nautical charts are communicated to the merchant vessel immediately, improving safe passage in critical areas. The RoBoVaaS project provides proof of concept for improving the operational flexibility of systems with unmanned underwater and surface vehicles, as well as cutting-edge sensor imagery. However, the human dimension will remain necessary, particularly for more distant operations and for safety precautions. The future system includes upgraded vehicles with improved autonomy, better underwater inspection sensor technology, and a completely new field of aerial inspection with ASV drone integration. The RoBoVaaS data cloud network is a solid foundation to build upon for future developments. RoBoVaaS is a solution for on-demand shipping services and near-shore operations for all ports, offering easy accessibility to European waters and enhancing maritime transport. RoBoVaaS is the future of maritime port operations.
Yeah, hello everybody, and welcome from myself again. Very happy that you all are here and found the time to make it to our live demonstration today of the project RoBoVaaS. So I want to quickly go over the 5 on-demand services again that we just seen in the video, and I will do that in a minute. But first of all, what were the core ideas that we had within the project? So to enable these 5 on-demand services, we also wanted to implement the complete service pipeline from a software point of view. So we developed our own RoBoVaaS web UI to really show the complete pipeline. And also very important for us were the testing of the services that we did. So we did small and large-scale testing, and the small-scale testing platform, the C-Line, you will actually see today live in action here at the HPA home port. And also we did full-scale simulation testing for the entry grounding service, actually with mariners to test the acceptance of such a service. And also we implemented above an underwater communication network to really allow these services to come to life. I want to go over the partners that were within the project. First of all, the 3-year project was funded by Matera and the national funding organizations. And there were 7 partners included. From Ireland, we had the University of Limerick and Sonasim. Then the University of Padua from Italy, and from Germany, the HPA as our main stakeholder, Kraken Robotics, and Fraunhofer Self, where I'm working. So let's go a bit more into detail about the services. So the ship hull inspection is the first one that I want to go into. As you've seen in the video, here we deploy an ASV. It can go close to the ship that needs inspection or requested the service, and then the RV is deployed. The RV can easily inspect the ship hull below the waterline and relay the information to the ASV, which is sending it to the RoBoVaaS cloud. We analyzed here optical inspection technologies as well as laser scanning technologies, which will be later presented in more detail. The key wall inspection is very similar to a ship hull inspection, only that we inspect the key wall. So the technology is the same that we deploy here, only that the RV is following along the key wall here, and the ASV can actually travel with the RV if the key wall length exceeds the tether length. So another use case that we investigate is bathymetry data collection. There the ASV can travel a predefined route, actually collecting depth data with single or multi-beam echo sounders, and this information is saved. Autonomous vehicles are quite useful here because they can routinely do this inspections, and all the data can later be visited and post-processed within the RoBoVaaS cloud as well. Data muling is our take on how underwater communication can be included in a dense area such as the port of Hamburg. Here it's interesting that we don't need an actual connection to the surface to relay the information to the ASV passing by if we are close to the underwater node. Therefore, we can deploy sensors in areas of dense traffic. And last but not least is the anti-grounding service. Here we deploy one of the vessels of RoBoVaaS, and it's traveling ahead of a merchant vessel that requested their service to actually give real-time bathymetry scans to the ship, and it can react to dangerous areas and plot a new course accordingly. So with all these use cases now presented, what is the RoBoVaaS vision that we actually wanted to implement? So we thought about how we can combine sensors and networks, the autonomous vessels, and actually develop and test these services within one coherent structure, which is the core vision of RoBoVaaS. And that you can see here again. So on the top line, we always have the user is requesting the service, one of the 5 presented, and then it goes through the user interface in RoBoVaaS Cloud and the shore center into the control center, and the vehicle can be deployed. Once the vehicle is deployed, the data is relayed in real time, and the user can actually see the results of the service or just watch it in post. The idea within RoBoVaaS was to actually implement the whole service pipeline and not only offer one of the components, so that we can actually cover the whole concept. And now, who could that be interesting for? This is where our partner HPA comes in, and now Benjamin from HPA will quickly say something about why these services can be interesting for a busy port like Hamburg.
Thank you, Vincent, for the introduction. I'm Benjamin Blank. I'm a project manager for the research and development projects at the HPA, which stands for Hamburg Port Authority. And as you might know, Hamburg is one of the top busiest ports in Europe. And research projects like RoBoVaaS are important for us because it helps us evaluate technologies, implement processes, and also look at regulations that need to be in place for these services to be employed and deployed. And all these results from these projects help us develop port services for the port of the future. Thank you.
Okay, thanks, Benjamin. And now I want to show you our web UI that we actually can show or book the service in for a user. So this is the complete service pipeline that we integrated from a software point of view for possible users. I hope the screen can be seen now that we have the sun here in Hamburg, which is actually quite nice. So this is our web UI that we developed, and once you logged in as a user, you can start to create a new service. And here you see the 5 services that we created within RoBoVaaS. I will just select environmental data collection here. And once the map is loading, I can import an area, for example. Here you see the home port of HPA, where we actually are located right now. And we predefined the route here, but we can actually edit that area as well. And then I can drag around the points and create a new route. And once I'm happy with the area that I selected for a survey, such as bathymetry data, I select this area to use. And then the operator actually receives this job request and sees all the information of this job. So, for example, latitude and longitude of the selected area and the points. Once you're happy with that, you submit it, and it's submitted to the RoBoVaaS server. And now the actual vehicle can be deployed, and this is what we want to show you today, actually live. So now we will switch to the water side of the Hamburg home port. Any minute now, there we are. And this is our sea line vessel that we developed within RoBoVaaS. So now that we created the service, the vehicle is deployed and will start its mission. Today we selected key wall inspection service, and we will see how the vehicle departs from the pontoon and actually go and do the service. So the sea lion, that's our ASV that we developed within the project as Fraunhofer CML to show that the small-scale demonstration of these services can be achieved within the 3-year project. The sea lion is 2.2 meters long and has a payload capacity of up to 120 kilograms. Right now we are in the underwater inspection configuration, so we have a winch on the front of the vehicle, an A-frame, and an exemplary blue ROV, which is a small ROV that we can lower into the water and then do a demonstration inspection. The sea lion can go up to 8 knots, and if we go at a cruising speed of about 6 knots, we can actually cover distances of 260 kilometers. So as a port as Hamburg, we can easily cover for such inspection services. So now we see that the sea lion has reached the quay wall. It will now position itself in the final ideal position to do the inspection. This inspection, of course, over this position, can be selected by the user beforehand. Once the final position is reached, the vehicle will enter the loiter mode and actually start the deployment of the blue RoV. Our current system here only needs to lift the blue RoV, which is 11 kilograms, but we developed the vehicle with other payloads in mind. To be very modular, we can lift up to 30 kilograms with the A-frame and winch, and the current tether configuration is 50 meters, of length. So now that you reach the quay wall, the vehicle has entered the loiter mode, and once the position holding is satisfactory, the launch procedure will begin. Okay, now you can see that the blue RoV is lifted, and once the system has lifted it to the top position and hold it there for a second, the A-frame will start to deploy. So within the project, we actually also developed another vehicle. So this is our sea lion you see right now, but we also developed the CML. If you're interested, you can see it at the home port. It's a predecessor and also capable vehicle, but we wanted to see how far we can push it. So we started the development of the sea lion actually only 10 months ago, and we are quite happy that we managed to show it today. So as you can see, the A-frame deploys, and once at its outmost position, the blue RoV is lowered. The blue RoV, as an exemplary RoV, has an HD camera on board, which we can use to stream video to the surface and show it in real time in the web UI. Unfortunately, we can't do that today because the visibility in the port of Hamburg is not allowing us to. So therefore, we will leave the vehicle in the water for a second, and then we start the recovery procedure. To show you how an inspection can actually look like and be performed, we have the actual demonstration of the sea vision sensor in a minute. So now the recovery procedure started. As you can see, the blue RoV is lifted out of the water again. The system automatically will notice when the top position is reached, and then the A-frame will start to retract again. While all this launching, the service and recovering is happening, the sea lion is holding position all the time against wind and currents, as you can see. So now the A-frame is completely retracted again, the blue RoV is lowered, and the recovery is complete. And we can say that a successful inspection has been performed, and the vehicle returned to its home base. Okay, and that's it for our live demonstration. If you want to see more of the vehicle, you can come to the home port and see it in the water. And now that we have seen how the demonstration or the services can be demonstrated in the small scale over the whole pipeline from creating the job to actually launching and recovering the inspection vehicle, we will go into detail about the sensors then can be deployed. And there our colleague Alexander Duda from Kraken Robotics will take over.
Yeah, thank you very much for the introduction and showing the vision for the underwater the services on demand we are developing in RoBoVaaS. I'm Alexander Duda. I'm with Kraken Robotics and an industrial partner in RoBoVaaS. Kraken Robotics is a leading company in underwater 3D sensing. And together with our partners, we are working on getting our sensor technology pushed into new underwater services on demand I'm going to talk about in the next couple of minutes. So if you want to do underwater inspections, you have basically the choice between two different sensor modalities. So you can go for acoustical-based methods or vision-based methods. The main difference is that if you use vision-based methods, you can get up to 100 times more resolution than you get with acoustical-based methods. However, you need good visibility. So depending on your mission profile, you have to fall back to acoustical methods. Assuming you have good visibility, you can use C-Vision, an underwater 3D scanner that can scan underwater scenes with sub-millimeter resolution. And I will give you a short introduction into. So the sensor system is built with two identical pods. Each pod is equipped with a low-light camera that runs at 120 frames per second. That is equivalent to 300 megabytes per second that we process on each unit. The data are either stored on an embedded PC or can be streamed to the cloud to the operator. The system has also a 3-color laser, so you can choose the color depending on the environment. So for shallow water, for example, you usually pick the green laser that you can currently see in the video. And for deeper sea, you can use a blue line to get greater distances. The laser is perspectively distorted by the scene, and we use that information to triangulate the scene depth with sub-millimeter accuracy in distances up to 6 meters. Both pods are electronically linked, so we can add additional pods if required. For example, if you want to measure undercuts, we can have 3 or 4 pods lined up. We can also add high-power lasers to extend the range to up to 15 meters if required, depending on the turbidity. The whole system is controlled via web interface and streamed to shore if required. So we have already some missions where the operator is actually not on board, but is sitting in the office to control the system. That is now the most simple use case you can imagine. So if you want to do underwater ship hull inspection, you can imagine that you have to deal with relative motion between the sensor system and the ship hull. And for that, we can illuminate the scene with a red light to do motion tracking while the system is scanning with a green laser. So we nicely separate both modalities in the spectral domain to get the lowest crosstalk possible. We also developed a new system so that the system can run in bright sunlight without saturating the camera system. To show the system, we went to Ireland to do some scans because in Hamburg, of course, you have to fall back to acoustical-based methods due to the turbidity. And now I will pass over to our project partner from Chris, who will talk a little bit about the mission we did in Ireland.
So, good morning. So I'm Jared Dooley. I'm based at the University of Limerick in Ireland. And our role within the RoBoVaaS project was to develop the underwater robotic systems which can carry the Kraken imaging systems underwater. So this is our ROV system here that you can see. This is a smart remotely operated vehicle. So this is delivering the imaging system to the dock area that we want to image, are to the ship hull area that we need to image. How this differentiates from typical ROV systems within the industry is that we can control this system automatically. So generally, ROV systems are controlled manually by a manual pilot with 10 years experience. But what we do is we develop autonomous systems so that the system can inspect itself and to be able to accurately navigate and control the subsea environment. So this is the ROV. It's called IROV, and it's 120 kilograms. In terms of the navigation and control instruments that we have on board then, so we have the core of the technology is an INS system, and this has 3-axis accelerometers on board, and it can estimate its movement underwater. So before we dive, we take a last known GPS position, and then we're doing dead reckoning on the system to calculate our position as the ROV moves through the water. And then this is the imaging system that we deployed onto the ROV for the RoBoVaaS system. And then this is our control platform that we developed. So we can do fully manual control of the ROV to fully autonomous control. So we can control, say, depth and altitude, heading control, and position control. So there's various other smart control systems built within the ocean ring system is what we call it. And then if we just have a look, so we do testing and different things in wave tanks to understand how the ROV system can maintain its position in waves and currents on the water. And then we developed a control system to be very accurate in terms of its navigation and control. If we think about the laser imaging system that we have on board, so we can do sub-millimeter resolution imaging from the laser system, and we need to have an accurate navigation and control system that will match that resolution. So this is the integration. So you can see the Kraken system mounts onto the front of the ROV. So we have a sea vision system on either side, and then we bring that data up topside through a small umbilical. So you can see the umbilical here goes to the top side. So the umbilical then is provided notionally from your surface vehicle, and this provides power and comms to the underwater vehicle and to the onboard sensors. So this is our system in operation in Ireland. So you can see we're imaging here at dock wall, and you can see the stability and control of the ROV itself. And the better the control and stability of the vehicle, this relates then to the quality of the imaging data that you get back from the sensors. So you can see the motion of this vehicle on motion stability is very good. So you can see as the scan goes across, then we're collecting that data, and we can reconstruct that into a 3D image of the environment. So we can get sub-millimeter resolution of that dock wall. This is the area that we tested in Ireland. So this is a small area that we did trials for the RoBoVaaS system. So we did dock imaging of walls, and we also did ship's hull imaging in this area. So a quick video of what we achieved through the imaging system within RoBoVaaS. So this is the area that we tested in. So the depth of the area goes to about 30 meters. And then throughout the 2 days of operations for the RoBoVaaS, we imaged quite an extensive area within the dock and also around the surrounding environment of the test area. So I can just skip on some of this. So this is a control system then for the IROV. And then you can see we're just feeding the umbilical down. In this instance, we're not launching the ROV from the surface vehicle, from the ASV, because we didn't have that on site in Ireland. And also the ASV needs to be quite larger from what it was at that time. So this is our operations. And this is a scan of an area within the test site. So we scan the area, we're basically doing a 360 turn on the ROV to scan the areas underneath the ROV. And you can see the laser line here as we go across. And these are the types of images that you can achieve with this system. So you can see the quality of the data sets are second to none. The resolutions there are sub-millimeter resolution. And in terms of achieving what you need to achieve for inspection of port infrastructure or other infrastructure, such as what's common within a port, the resolutions that we can acquire from this platform are quite unique. So I guess that's my introduction into the ROV systems, and which can take the payload platforms that we did for the trials within the RoBoVaaS system. I'll pass you back then, back up to the organisers there. So,
Thank you very much for the demonstration. It's very interesting. And now we're joined by Filippo Campagnaro from the University of Padua and James Riordan from SonarSim. We're going to have a few panel discussion or a few questions right now. We will throw it out to the audience if there are any questions later. But maybe starting with a general question, how does the work of RoBoVaaS enable the port of the future?
Thank you for your question. So, first of all, we deployed an integrated, robust network in order to control all the vehicles that were performing the services during the RoBoVaaS project. So we used long-range radios antennas that could allow us to control surface vehicles up to almost 1 kilometer from the closest base station, while these antennas did not work for underwater communication. So in order to communicate with underwater vehicles as well as with the nodes that we deployed under the sea, we had to go with sounds. This is why we use the Ahoy modems that are acoustic modems developed by the Technical University of Hamburg in order to enable the communication between underwater vehicles as well as with the underwater sensor that we deployed under the water. And only with such an integrated network composed by above water and underwater systems, we could enable the services of the port of the future.
Yeah, thank you, Filippo. And I think I can add that with this network integration, but also with our service pipeline that we integrated and the vehicles, the ASV that we built, we could enable the complete pipeline of services and therefore show that these services can work and can be brought to possible customers in the best way.
One of the things when we're speaking about the RoBoVaaS services is we're talking about ship anti-grounding, navigation, maintenance, inspection. They're deployed in a very safety-critical context where the challenge isn't so much to get them right, it's that they can never go wrong. So to prove the robustness of the system before we deployed into the real world, we built a very comprehensive full-scale simulation model, in particular for the ship anti-grounding service. So we developed a full model of the hydrographic survey process, unsupervised and deployed onto the unmanned surface ship. But we did it in such a way where most of the components were actually real world. So our partners, Hamburg Port Authority, provided real data of the port environment. We were able to build a scenario around that. Our partners, Fraunhofer CML, were able to replicate the ship bridge and the port and harbour interfaces. We benchmarked the system according to the industry standards and used real mariners in the investigation. So this allowed us to escalate the complexity of the system, prove and validate the safety aspect before progressing to the real-world deployment.
Great, thank you for that. So we've heard what you've done to date. In terms of looking ahead and kind of enabling these kind of operations in the future, What needs to be done, I guess, from a port authority point of view, but also just maybe more generally in terms of enabling the environment?
So thank you for this question as well. And of course, for enabling the services presented in RoBoVaaS, you need an integrated infrastructure for a wireless network that should be quite robust. And the Port of Hamburg is already doing a lot in this context thanks to his 5G infrastructure that is already deployed here. And in the future, we envision to integrate in the existing network also communication system for IoT devices, as well as low Earth orbit satellite systems and underwater acoustic and optical communication technologies. That it's a little bit what stays behind the paradigm of 6G that aims to integrate different types of communication systems in order to reach almost 100% global coverage. And in my perspective, 6G should be extended also considering underwater communication in order to enable all the services for the port of the future.
And I think continuing that, I think a lot of the future vision for the port of the future leverages the rollout of 5G and 6G communications, and future ports will see swarms of autonomous vehicles working cooperatively across land, air and sea contexts. So the RoBoVaaS solution focuses very much on the underwater mapping, inspection, survey, navigation and so forth. But as you'll see with the exhibition stand below, a lot of the sister projects and projects that have grown out of RoBoVaaS are now focused on also integrating the aerial aspect of this. So for example, integrating drones with the Sea Line and with the CML vehicle and building on top of RoBoVaaS to unlock further multipliers and to develop the safety assurance technology that's required for these rollouts.
Yeah, I can only agree with my colleagues and only want to add that to use the network and deploy aerial drones, for example, in the port, we need a good structure, a good base vehicle to deploy that. And I think that's where the RoBoVaaS ASVs come in, and in particular the Sea Line that we developed to create this modular platform to deploy any technical solution that we need for the service that any of us or the audience can actually envision. And we are happy to make that possible in the future.
Great, thank you. And maybe sort of linked to that, I mean, I think you've already touched upon it, James, a little bit, but in terms of maybe in 5 years' time, what are we going to be seeing as kind of additional technologies or platforms rolled out, sort of considering where we are now?
I think one of the key drivers is to remove the human from the loop. So tasks that are very manually intensive, time-consuming, expensive, sometimes prone to error, that these become replaced by autonomous vehicle solutions that have improved scale, productivity, efficiency. And I think this is what we will see, that we will see very integrated, safe solutions that are plugged into the port professional workflow for routine survey, maintenance, inspection, collision response, and so on. There's a long way to go on this. It is a very large multidisciplinary challenge, but I think that is the general trajectory of where it is going, and there's a fantastic foundation here in the Port of Hamburg, as you can see with the projects being exhibited in Homeport today.
Great, and then maybe link to that for Filippo. So in terms of the technical issues, I guess, with communications to these platforms, is there particular technologies sort of coming out in the coming years that will make these kind of operations easier, or is it a case of just improving upon the existing technologies?
It really depends also in which area of the world we are talking about. Because if we talk about what is available in the Port of Hamburg, that is something quite unique for ports. You can, of course, rely on very good 4G connectivity, 5G connectivity, and deploy customized radio networks only when it's required. Instead, if we talk about ports in South America, it's totally different situation. So there, you need to deploy a network from scratch. And this means that the radio system deployed there should be done for the services and thinking about if the deployment you are going to do will be enough to support them.
Okay, and that actually brings me to my next question, which is maybe for Vincent, or I'm not sure. So Homeport here is quite a sort of special setup. It's a space that's designed to allow startups or companies to test their new technologies in kind of a real-world environment. How do you feel that Homeport or these kind of centers help accelerate these kind of deployments of new technologies?
Well, I think what we for Fraunhofer CML Fund or RoBoVaaS project that have a physical place to interact with other companies, as we just did in the last days, is very fruitful to see what other services could be implemented and where are the synergies between a system that we developed in RoBoVaaS or other players in the market. So have these areas close to the port where we have to interact, for example, with the ferry, which is coming every 50 minutes. It's a real-world scenario that we have to deal with here when we want to test. That shows us where we have to improve the systems and where we can actually push to be at a place where we want to be in 5 years. And maybe to come back to that question within the 5 years, as James said with the deployment of aerial drones, I think the most complex challenge is from the vehicle point of view that we integrate these different vehicles into one coherent system, as we tried within RoBoVaaS with the web UI, that we don't have to start on the technical implementation layer for the end user, but give them a service that they can use as a service, as we tried within the project.
Great, thank you. I'm wondering, are there any questions from the audience at all? Not right now. In regards to the depth mapping for large ships coming in, how long does that take to turn around as a service? So, the ship arrives, moors offshore, and then the ASV gets deployed. What's the turnaround time for this sort of in total?
You mean like deploying the ASV to actually do the service, such as ship hull inspection?
From the point where the service is requested, maybe. So how long is a ship going to be waiting for the full report?
Yeah, that's an interesting question. So maybe we take the Port of Hamburg as an example. So when the ship actually enters the River Elbe to come to the port, it takes approximately 10 hours. So that's quite a long lead time to request a service such as ship hull inspection. Our system is set up so that it can be, once the user really sends out the service, it comes in real time to us and can be processed. Then it simply depends on how many ASVs you want to have in your fleet to actually offer that service. And where, let's say we start from home port and have to go to another area in the port, maybe half an hour to go there, and then depending on the ship length, we can be done in 2 hours, I guess. So that's a very rough estimation here, but yeah, maybe that's an estimation that I can give.
Okay, so it's very dependent on the particular case, which is fair enough. Maybe to pick up on something you said, James, where the aim of these robotic platforms is to, kind of replace human error in some ways, or improve safety standards. I guess with any of these kind of platforms which are reliant on technology, there still needs to be a human involved in terms of analyzing the data and interpreting it. Can you maybe talk a bit, and this is for any of you, in terms of where the human side ends and the robotic side sort of begins, and what's going to be required moving forward? Because I guess it's a balance.
I think we're very similar to the situation in automotive, where the regulators will accept assistive technologies, but they want to see more comprehensive validations before they will allow full autonomy. So in use cases, say far out to sea or in agricultural, where you're far away from hazards and people, they're allowed. But when you start coming into a densely populated, cluttered, complex environment like a city port, this is where the system proving becomes critical. And there are a number of regulators that are involved in this. At a European level, it's the European Union Aviation Safety Agency, there's the International Maritime Organization, there's regulators in each individual port. The data standards have to adhere to the International Hydrographic Office survey standards. So where we're at the moment is there's human on the loop there to intervene if there's an emergency, or the machine needs the human to take over cognitive and physical control. What the next challenge is to be able to embed that hazard perception and sense and avoid and sense and detect onto the vehicles themselves, and this has to be done in a very safety assured process. And this is something that we were focusing on very heavily in RoBoVaaS through these full-scale simulations, moving to mixed reality, and then moving on to full real-world demonstrations.
Anybody else, anything to add on that?
I think James covered as well with what we did in RoBoVaaS with the full-scale simulations and actually inviting mariners into a test environment where they can use the ship handling simulator to see how the system, like the anti-grounding service, would work and give us direct feedback what we can improve so that the acceptance is higher of these services.
So as these platforms develop in terms of their intelligence at analyzing the current situations, I mean, again, this is sort of looking ahead, how involved, or maybe how many people, say for the Port of Hamburg, how many people are going to need to be there sort of managing the RoBoVaaS operations on a day-to-day basis, if this were to scale?
Well, that's an interesting question. That depends how many vehicles you want to deploy and how much autonomy you give to the system. So if you say, I think that can't be answered very precisely from our point of view. It depends how much you trust into the system and how much autonomy you give into the ASVs, for example. If you say one operator can control 10, 20, 30. But yeah, that's possible. The technology is there, as we just heard from the sensor side, the network technology. We created the IT infrastructure and the vehicles are ready, I guess. So it depends how well do you trust into the technology.
Yeah, maybe the question should be rephrased with how many people could you avoid to use performing such services with a manned system instead of going there with a manned vessel full of people and divers that have to dive down, risk their life, instead of making it with a unmanned vessel that can be act either a little bit autonomously or piloted from a remote.
Okay, that's a good way of phrasing it. So, jumping back to something you said, Filippo, in regards to ports or other ports around the world, which are maybe less as advanced compared with Hamburg, in terms of the other considerations that you need to make for these kind of new areas, I guess in terms of regulation, or you've already talked about the technology, but maybe trainings and skills. Can any of you sort of talk to how you plan on approaching that moving forward?
I think to continue what Vincent and Filippo were saying, the key benefit of a solution like RoBoVaaS is it reduces the operational cost of the service, because you reduce the requirement for ships and pilot vessels and so on, and the data collection and the monitoring becomes deployed to autonomous surface ships, but in a way that it can be integrated into ports that have limited communication infrastructure and maybe can't afford to do very comprehensive hydrographic seabed survey. So I think this is one of the key drivers behind the RoBoVaaS service, is that it's, as well as being one of the most accurate and productive, it's also one of a more cost-effective approach to doing this.
And in terms of deployment, do you have other ports sort of in the works in terms of where RoBoVaaS will be deployed, sort of coming up, or are you able to talk to those at all, or a plan sort of moving forward?
So I think we are happy to deploy RoBoVaaS with any port that is interested in it, but within this project we collaborated with HPA and the Port of Hamburg in particular to make it happen in a specific area, test environment.
Okay, thank you. So I think we're going to sort of start wrapping up now, but I'd ask you all if you have final comments or thoughts based on, seeing the demonstration and what you've taken from the ITS Congress so far as well. So who'd like to start with that?
Okay, I start. So I really want to underline the fact that all the goals of the RoBoVaaS project have been accomplished thanks to the fact there has been a strong coordinated funding action that allows different partners from industries, universities and port authorities to work together. And so thanks to this joint effort, we could accomplish prove the feasibility of all services presented in RoBoVaaS.
I think one of the key success factors for RoBoVaaS was also these challenges are large interdisciplinary collaborations, and the RoBoVaaS consortium internally had large end users in the Port of Hamburg, there were industry partners, there were technical and research universities. The project engaged policymakers and civil society. And I think this is one of the key factors for projects like this that have to take in that large interdisciplinary collaborative approach going forward, and this is a model that has worked very well in RoBoVaaS.
Yeah, I can only agree. I think we did a good job reaching our goals that we set out 3 years ago, and already created a lot of synergy effects with other projects as Rapid and built quite a lot of momentum. And we are happy to use that momentum and want everybody to invite to join us, to not miss out on the trend for the port of the future.
Great, thank you. So with that, we'll say thank you to Vincent, Filippo, and James. That's going to conclude the session for this morning. We've got Spleen Lab coming up at 11:30. If you want to...
Sorry to interrupt you. Thank you all for coming here, the people who came in person in particular, especially with this cold weather today. If you want, we have some coffee and snacks downstairs, so invite you to come to our container booth out down there, and you can see the sensors and the ship in real. So join us for any discussion that you want, and thank you for your attention. Luis, thanks.
Yeah, exactly. So you can come and find RoBoVaaS at the container at Homeport. A reminder that you'll find a recording of this session on YouTube. So if you want to review it or share it, please do. And with that, we'll wrap up the session. So thank you very much, everyone.
As the world becomes increasingly digitalized, so are ports and maritime transport. Sensor data collection is increasing safety and security measures and operational efficiency, whilst technologies will continue to reduce accidents, economic costs, and carbon emissions. The Robotic Vessels as a Service, aka RoBoVaaS project, is about demonstrating services that connect cloud-based software infrastructure, a fleet of autonomous vehicles, and innovative sensor and inspection technologies to show the potential of on-demand maritime robotic services for larger-scale deployment. When a user requests a service via the RoBoVaaS cloud, autonomous surface vehicles, ASV, are deployed to collect data for the given service that is relayed back to the cloud. Possible users include ship captains for anti-grounding, ship owners for hull inspection, port authorities for key wall inspections, or terminal owners for data collection. The RoBoVaaS demos include 5 services that provide data to the users. Ship hull inspections using the remotely operated vehicle, ROV, launched from the ASV, can inspect and locate possible damages precisely without any risking diving operations. Key wall inspections can be performed by both ASV and ROV as routine inspections with high detail sensors, thus reducing the operational costs dramatically. Data muling relies on underwater acoustic communication to transmit data, which is useful in port areas where buoys or tethers can be obstacles to vessels. Bathymetry data collection uses ASV to map depth deviation from nautical charts, allowing for up-to-date information in areas with high tidal variation. Anti-grounding has an ASV travelling ahead of a vessel and collecting depth data in real time. Depth deviation from nautical charts are communicated to the merchant vessel immediately, improving safe passage in critical areas. The RoBoVaaS project provides proof of concept for improving the operational flexibility of systems with unmanned underwater and surface vehicles, as well as cutting-edge sensor imagery. However, the human dimension will remain necessary, particularly for more distant operations and for safety precautions. The future system includes upgraded vehicles with improved autonomy, better underwater inspection sensor technology, and a completely new field of aerial inspection with ASV drone integration. The RoBoVaaS data cloud network is a solid foundation to build upon for future developments. RoBoVaaS is a solution for on-demand shipping services and near-shore operations for all ports, offering easy accessibility to European waters and enhancing maritime transport. RoBoVaaS is the future of maritime port operations.